All right, let's solve some of these textbook problems. So actually, we've only got 3 left, and the due date on this wasn't until uh, this Friday, a few days from now. But if you want to get this off your hands today, then you can, because we'll be finished here in a few minutes. Okay, so chapter 18, there was this was on refraction. There was one more we have to do. Actually, I think paces out pretty good because pretty good review here. You guys remember Snell's law, refraction? So what have we got here? Swimming pool lights. You guys can see this. A light source is located 2 meters below the surface of a swimming pool and 1.5 meters from the edge. Okay, exactly like this picture. Ooh, here's the light right here. So we've got some light beaming out, light rays in all directions. At what angle does the light reaching the edge of the pool leave the water? So we're looking at one particular light ray that's following this path. It's going to break out from the surface of this water going into air, and it's going to refract. So it's going to change direction. And then the follow-up question, does this cause this refraction that we're going to figure out first, viewed from that angle appear to be deeper or shallower than it actually is? So first question first, release the second one. Okay, redraw, zoom out. Number 73. As long as you guys are following, then it should be easy to knock this homework out and some easy points here. Okay, so we got the bottom of the swimming pool. Looks like it's 2 meters deep. And something like that. Okay, so we got say underneath the pool, got the wall of the pool, and the floor, the ground above. Right? There's probably right about here-ish is this pool light. Shining into the light. So we've got the surface of the water is right about here, surface of the water. Okay, give it a little look. Okay, and then take let's go with some, need to label some distances. We got 1.5 meters here and 2 meters here. One of the light rays, now light rays, of course, going in all different directions. You can see the light from all different points of view, but one of those rays goes this direction. And right at the corner here. Okay, then when it leaves this water, because this is water, and the bottom is air, we should label those water versus air. It's going to refract. Now, remember, we've been measuring angle of refraction with respect to some normal line. That's the normal line right there, right? Josh, find that's normal to, that's to say perpendicular to the surface. Okay. Now, I want to see show hands how you guys are thinking that this light ray will refract. I'll narrow it down for you guys to 2 options. It's either going to bend up like this, or maybe it actually bends like this. Okay, does it refract this way or this way? I would say option A or option B. Okay. Show hands. How many guys thinking it's probably going to be option A, going to refract this way? Who says option B refracts like this way? Yeah, okay. All right, see a bunch of hands up. You guys are right. Because it's going from something with a high index of refraction. So this is like n equals 1.33 to something with a low index of refraction. N equals like 1.0 for air. Yeah, it will refract sort of in this type direction. Yeah, no, it's at the exact angle. We'll do a calculation, figure it out. Right, so I'll call this angle on the side of the water. I'll call this the angle on the side of the air. Notice I labeled this these with respect to that normal line, perpendicular to the surface. Hey, maybe there's well, let's go draw a stick figure. Maybe I'll say that for part B though. Okay, so first part first. What is this angle? The part A says, what is that angle? So let's go to Snell's law. You guys remember Snell? We got index of refraction times the sine of the angle on that side. Well, that product is equal to same product on the other side. N1 sine theta 1 equals N2 sine theta 2. Okay, now, okay, we know what the index of refraction is for each material. I got it here. Water is 1.33, air is 1.00. Okay, pop, so that's okay. Now, sine of the angles, there's a couple of ways that we can handle this. One path you could go is to actually solve for this angle and then plug it in that way. A shortcut you could do if you're pretty good at geometry is navigating geometry is to look at, this looks kind of like a right triangle. Maybe saying, well, sine is the ratio of two of the sides. So just a couple of different perspectives on how to solve a problem like this. I mean, one of the things I want you to get out of this class is, how can you solve problems? Maybe what are different routes to solve them, what are different approaches you can take. So let's do that first way first. Actually grab this angle. Do you guys know how to figure out what is theta sub w? What is this angle in the water? How about this? Do you guys see a right triangle right here? Nice right triangle. Okay, so we've got the two legs of the right triangle. Oh, guys, if you know two legs of a right triangle, is that something to do with sine, cosine, or tangent? Tangent, yeah. Opposite over adjacent. How about this? How about this? Sine of theta w would be opposite over adjacent. Or I'm sorry, not sine. You guys just told me tangent. Or tangent. Tangent of that angle would be opposite over adjacent. Sine, of course, is opposite over hypotenuse. Okay, so then how do you isolate theta? What's the step to do what to both sides? Inverse tan. Yeah, you guys remember like tangent of an angle will spit you out a ratio. Inverse tan of a ratio spits you out an angle. Same thing for sine and cosine. So we want inverse tan of 1.5 over 2. The meters cancel. See what that is. What is inverse tan 1.5 on 2? Okay. So this angle is 36.9 degrees. Call that pretty close to 37 degrees. Hey, that's about 36.9, 37 degrees. Does that angle look familiar dealing with right triangles? It is a 3, 4, 5 right triangle. 3, 4, 5. I should have asked you guys before I went on this whole adventure. How many of you guys noticed that before I did that? This was a 3, 4, 5 right. Yeah, so some of you guys saw that. Because the ratio of legs is 3 to 4. 3 divided by 2, 4 divided by 2. So this one must be 5 divided by 2. You're like 2.5, if we cared about that. Okay, so that's kind of cool. So one thing you could do is you could take this, just pop it straight up in there, and then solve for this other angle to do that. But here's the other approach. Okay, so n of water is 1.33. So here's the side of the water. Is you could say, see sine, remember how the side, this hypotenuse must be 2.5 meters because it's a 3, 4, 5 right triangle. Okay. Sine of this angle could refer to opposite over hypotenuse, couldn't it? Which would be this opposite over this hypotenuse. So that'd be like a ratio of 3 to 5, either 1.5 or 2.5, or it's going to be a 3 over 5 ratio. Okay. Here, let me show that to you guys. What is sine of that angle that we just got? 0.6, which is exactly that fraction right there. On the side of air, index of refraction is 1.0, and then sine of theta on the side of air, and that's what we're trying to get. All right, so what is that times that? Let me swap both sides. So sine of what we're trying to solve for is 0.798. Okay. Oh, right. That was really close to fourth this, doesn't it? Huh. Right. That makes me think that something to do with this geometry above the water in the air might be also really close to the 3, 4, 5 right triangle itself. Right. Yeah. So what's inverse sine? So theta is inverse sine of that number. So what's inverse sine of that? I'm looking at 52.9 degrees. Okay. Remember 3, 4, 5 right triangle, like the other angle, this angle down here, is really close to 53 degrees. That's pretty darn close. That's to say that we're actually talking about this triangle up here. Okay. This angle right here is equal to 52.9 degrees. I'm just saying that it's really close itself to 3, 4, 5, but it's not exact, but it's pretty close. All right, so that's the answer to part A. Part A. Okay. Oh, and you guys see how 52 degrees, obviously more than 36 degrees. Okay, so yeah, that does confirm what you guys told me ahead of time, is it's going to refract in that direction. Okay. There's a follow-up question, which is if you're standing up here, right, so now it's time for a stick figure man, kind of drawing in some aqua ink. So here's my stick figure man, maybe, well, I guess he's pretty short, right? So here's some little kid. He's looking down in the water and he can see this light. He just barely sees it, right, over the lip at the edge of the pool. Right? You just barely see that light. Right? Hey, what if you did this? What if you drained all the water out of the pool? Right? There's no more water. Can this kid see this light anymore? No, his view is obstructed by all this going on here. Right? You wouldn't just put the water back in the pool. Ooh, now the light refracts so that he just barely can see it. Right? You can see it, right? But the way he would interpret it, right? I mean, if you're looking into a pool, doesn't it seem like the light's coming from like this type direction? Something like that? Almost like it would be kind of about here. Something like that, right? Because, well, light travels in straight lines, that's what looks like where it came from. Right? That's his perception. So part B says, does the light, does this cause the light viewed from this angle to appear deeper or shallower than it actually is? So the answer is what? Like shallower. Yeah, the light looks like a shallow pool. You guys have probably seen this too. So next time you're a pool situation, like go to the deep end, say, how deep does that look from above? It might look, so deep. And then you get in that water, look down, like, whoa. Once you're submerged, it looks way deeper than it did from the surface. That'd be true. Chapter 19. So on to the interference and diffraction questions. So one question for each of these scenarios. We've got a double slit experiment and a single slit experiment. Looks like set up. Oh, there's a nice tidy formula that goes with each one of these. See what the question is and how the variables can match up to this equation, how to solve this together. So start with this double slit experiment. Light falls on a pair of slits, 19 micrometers apart, or maybe say micrometers. Hey, that prefix micro, that's 1/11. I know 1/1,000 is milli. 1/1,000,000 is, that's what that is, 1/1,000,000. Okay, so 19 millionths of a meter. Okay, so two slits really close to each other. And 80 centimeters away from the screen and back. The first order bright band is 1.9 centimeters from the central bright band. What is the wavelength of light? All right. So that double slit experiment. This is something I told you guys about yesterday, Young's double slit experiment. Now it's really famous because at the time it seemed to confirm that light was in fact a wave and not made of particles. Now there's an extended version of that answer, which is light actually has a dual nature. It's actually sort of both, but this shows the wave properties because it will create this interference pattern, right? Which interference, constructive, destructive, constructive, destructive. You get a band that looks like this. Let me zoom in. You guys can see that. If you're at home watching a video, show you guys on the video that nice looking interference pattern. Yeah, take a look at that. Nice photograph there. So there's sort of the central band, maybe like, maybe that one's pretty close to. And then, hey, see how there's like a measurable distance between each of these blips of light? So that must be calculatable based on maybe something to do with maybe like this distance or how far apart the slits are or what the wavelength of light is. Oh, that's this formula right here. It tells you the relationships. So yeah, let's jot that down and go solve that. Number 47. Yeah. So we got wavelength. That's what lambda is, right? Wavelength is equal to, okay, we got an x times d divided by L. Let's see what each of those variables would pair up with or what would be reasonable. So I'm thinking that this x refers to the distance between each of these blips of light on this interference pattern. Okay, so that's x. Right? It looks pretty consistent, the distance between those. Okay. Then d would represent these 19 micrometers in this case, right? 19 millionths of a meter difference between these two slits. And L, that's the distance to the screen. Okay, so And since the question is, what is the wavelength? This is already set up in a way that we're not really gonna have to do any algebra. We can just do arithmetic, just plug stuff in. So the wavelength is, let's see, X was given as 1.9 centimeters. Right. So 1.9 centimeters. I want to be careful with this because centi, maybe I have to convert to meters. Okay. So centimeters, I could either say times 10 to the minus 2 to turn it to meters. I did it earlier in class like that. Or I could say something like this. Say, 1 meter is 100 centimeters. Do a little dimensional analysis type thought. Right? Yeah. Centimeters. Meters. Times the distance between the two slits is 19 micrometers. So that's 19, well, I'm gonna do this. I'll do this one in terms of like scientific notation. Micro, that's 1/1,000,000. That's 10 to the minus 6, right? Meters. Okay. I know I'm sort of mix and match in different methods of conversion, but 2 different ways you do it. Okay? Either dimensional analysis or scientific notation to convert back to meters. And then the length was given as 80 centimeters to that back screen. So 80 centimeters. Maybe I'll do this one as scientific notation too. 80 centimeters, that's like 80 times 10 to the minus 2 meters, something like that. Okay. All right. So anyway, today I get something in meters because this meters cancel out. I get meters, which could measure a wavelength. And so we just did a unit check. Meters measures wavelength. All looks good so far. Let's see, what is 1.9 over 100? All times 19 times 10 to the negative 6, all divided by, open parenthesis, 80 times 10 to the negative 2. And the answer is, oh boy, that is a tiny number. Looking at 0.000000451. Remember, the unit is meter. Okay. Actually, tell you what, I think that looks like a really good answer. I'll show you why from both. That's written out long form, but maybe there's other ways you could write this too. What would that look like in scientific notation, for example? Scientific notation. Can you guys write scientific notation before I do? Did you guys write this like 4.51 times 10 to the what? -7. Yeah, because 1, 2, 3, 4, 5, 6, 7. The decimal would be 7 places removed. -7 meters, right? Remember, the negative just means the decimal rolls back to the left. Or actually, there's a way I like even better than scientific notation for this wavelength. Okay? You could also call this 451 what? With a prefix. It's not millimeter, it's not micrometer, it's nanometer. Yes, nanometer, because nano is 1/1,000,000th. That's 10 to the minus 9. Okay. So 451 is it. Oh, 451 nanometer. Hey, you guys remember EM spectrum? Say you have longer wavelengths and shorter wavelengths. The visible portion of it, you can see anywhere from red, which is pretty close to 700 nanometer wavelength, to violet, which is pretty close to 400 nanometer wavelength. Nanometer. Okay, so this actually is visible light. It's a particular color. If this is red on this end, and this is violet on this end, then our light ray looks probably pretty close to what color? A lot closer to this end. I think it's probably going to be like a bluish color. This is probably like a blue light. That's what I'm thinking. That makes sense. All right. And one more to go. Number 52. So now we got a single slit experiment. So just by the way, double slit experiment, you can try yourself. Just take a card, play a couple slits. I would do this as a demo, but don't really get a good camera angle on this. But shine a light through, and then should see like an interference pattern. Monochromatic light. pass through a monochromatic, so mono one chromatic, like chromatic by colors. One color light passes through a single slit with this particular width, 0.01 centimeters. Woo, and falls on a screen 100 centimeters away. We also call that 1 meter. If the width of the central band is 1.20 meters, what is the wavelength of the light? Well, if we're talking about a single slit, we're not really going to get an interference pattern. Remember, interference pattern, we're looking for something more like, well, maybe like the last question we did, like double slit, where there's two sources of light that interfere with each other. That's what will create that kind of pattern. So if you just have a single slit, that's probably going to be more like there's just a single band of light at the other end. So we've got our screen at the other end. For making sense of this, and let's say we get a band of light that looks something kind of like this, for example. I'm just blowing this way up. So there's a band of light, okay? And now it's going to have hard edges like this. Well, that's where you get into like, diffraction, but let's just say, sake of argument, that we can measure something like that. Okay? All right. Now, why did I put that dash down the middle? Because I'm about to connect this back to the formula they gave us. The formula they gave goes like this: 2x1 is equal to 2 times the wavelength times L, the distance to the screen, all divided by W, the width of that that single slit opening. Okay? Now, I see a couple of 2's here. I mean, when you math, then you right away want to cancel those out. Like, why is there a 2 and a 2 on both sides? Because from this single, from the central dash line to the edge of this band, that's called X. Okay, so the full width of this thing would be 2 times X, wouldn't it? 2x1? Okay, that's what that is. And that's actually a single number they gave us. They just gave us that whole number. They said that is 1.2 centimeters. So that's what that is. Okay. And we're still trying to solve for wavelength, just like last part. Okay, so a little bit of algebra involved. Let's put some numbers in here. So 1.2 centimeters for this whole piece. How about 1.2 times 10 to the minus 2 meters, because that's 1.2 centimeters, right? Centi, 10 to the minus 2, 100. 2 times the wavelength we're solving for, times L. L is the distance to the back screen, which was 100 centimeters. Oh, let's go ahead and convert that right now. Just call it 1 meter, because that is 1 meter, right? 1 meter exactly. All divided by the width of that single slit, which is 0.01 centimeters. That's 0.01 times 10 to the minus 2 meters. Centi, 1/100. That's the scientific mode. Exponent way to think of it. Okay, so if you want to solve for this lambda, just do a little rearrangement and cross multiply it this right here. So I'll just write what I have already. So this many meters multiplied by this many meters, all divided by this 2, and also this unit meter. Okay. Meters, meter goes away. I still have this meters, which describes the wavelength. All right, let's plug and chug. 1.2 times 10 to the negative 2, 0.01 times 10 to the negative 2 also, all divided by 2. Yeah, that looks right. Wavelength is 0.00000006. If we're allowed to sig figs, I'll go ahead and throw on another 0 here because we can know that level of precision, and this would be meters. Now, I remember the answer to the last question. It was also decimal followed by 6 zeros and then some numbers after that. This looks like the same order of magnitude as the answer to the last question, doesn't it? Which might mean that this wavelength is also possibly in the visible spectrum. What else, guys? But I'm sure you could get this anyway. This is 6.0 times 10 to the what? -7, just like before, meters. I could also call that 600 nanometers. 600 nanometers, that's also in the visible part of the spectrum. So your eyes could detect this. And what color approximately do you think it would be? 600 nanometers. Yeah, I'm gonna guess maybe orange. I have not quite checked that, but that's almost certainly, it's in the ballpark, probably around kind of like an orange type color. Guys, good there? All right, So we have covered all the problems on the page. So just turn that in sometime between now and the weekend, and I'll give you guys some points from the grade book. So let's flip over and do some more demos.